everyone, welcome to this tutorial. In this tutorial, I'm going to show you how to perform glycol dehydration of our natural gas using Aspen Hysys. First step to perform this glycol dehydration tutorial, we need to go into the Aspen Hysys software. It's just loading up. I'll give you a brief introduction on what glycol dehydration is. Glycol dehydration is a liquid decision system that removes water from natural gas. Typical glycols that are used in industrial applications include triethylene glycol, diethylene glycol, monoethylene glycol, and tetraethylene glycol. In this tutorial, we are going to use triethylene glycol to perform our glycol dehydration actually. So after we entered, let's say go on to new. So this opens up a screen. The first step in performing any Hysys simulation is to create a component list. So that when you click the component list in the properties toolbar, that opens up a window like that. Now what you can do is say add on it, and it's got different components in it. So the first thing is methane. Click on that. You double click on that, that gets added. Second thing which we wanted to add is ethane, that gets added onto it. Just waiting for this installation to finish. Should be quick. Maybe I can still play around with this. Yep. So our natural gas is for the term project which we are going to use is pretty simple. It's methane, ethane, and then we are going to have H2O in it. How this glycol dehydration fits into your term project is, I think you guys already know it, but just give you a quick background. You model the reservoir using the petrol software. Then you use uh, Olga to model the pipeline side of things. And from the pipeline or from the separator or from the slug catcher, you take it on to the glycol dehydration. So your inputs into the model are going to be the outputs from the Olga model, if you understand what I am trying to mean. After you've added methane, ethane, we are going to also have water in it because there is no separation. It just goes off from an FPSO. So let's say water, add water to it. And because this is the master component list, we need to add triethylene glycol to it as well, because that's a part of the that's a part of the components in the simulation as well. So let's add triethylene glycol. That's done. And the next step is to select a fluid package. Again, go on to the property section, click on fluid package, that opens up a window. Click on add and select the fluid package. For this glycol dehydration, we are going to use the Peng-Robinson equation of state. We say that, and that's about it. You don't have to change anything after that. After these things are all done, now we go into the simulation environment. So the simulation environment opens up. It opens up as a flow sheet, and you can see a palette object, a window or a toolbar basically, right next onto the window. You can just move it to the right side of it so that that's helpful for you. So when that's done, so the first step is when you get your gas or saturated gas or gas with water in it, you pass that through a separator. You separate out the water out of it, and you take the gas from that separator, and that goes into a absorber. That absorber is where a triethylene glycol comes in, and that's where the dehydration happens. And that absorber is modeled here as a distillation column. So you send in triethylene glycol, and you send the gas from the first bit of separation you do, and they mix together, and you've got a number of stages which you can define for your distillation column, and that results in the separation of water. Like water gets absorbed by the triethylene glycol, and you get gas of as low composition as possible. So that's about it actually. So the next step is to how do we go on doing this in Hysys. So we want to add in a separator, as I discussed before. This brings up, you double click on it, and that brings up a separator for you. This has a font size which is too big for us. So we can go into the format window, maybe, and we could say that as maybe 6 or something like that, or say 5. Yeah, that's much more visible. That's good. So you add in a separator. Now you need to add in a feed gas to the separator. So you add the material stream again, that comes up. Change the format side of things, move that to a position where you would like it. So that's a feed, so I moved that to the left hand side of it. So you could rename this bit here. I'm going to rename this as the wet gas. You need to add a certain, you need to define the temperature and pressure at which they come in, and the flow rate which they come in as well. These should be all outputs from your Olga model. So the temperature which we are going to assume today is about 35 degrees Celsius. Pressure we are going to assume about 69 bar. So the molar flow I'm going to assume, and this again will be an output from the Olga model. So I'm going to assume 1743. And you could see here the fluid package has already come through. That's the basis one. So that splits into, so you need to add in two more streams. One is the gas stream, another one is the water stream that would come out. So you add in a material stream. Yeah, and change the format, font size, fine. And then that is going to be the gas to the absorber column, absorber, name it like that, then add in another stream. Yep, that's coming already, and name this as the knockout water. And then you go on to the separator, just name it as a separator. Then your inlet, you could select what you wanted to add, say wet gas to it. It's not actually change the name of the streams I wanted it to change. So I'll go and change the names of it. Before that, I'll connect that. It's going to be liquid outlet 2. That stays connected. So now I want to go and change the temperature. Not the temperature, the names of it. So water. This is going to be gas to absorber. Click the next one. That's not working. Gas to absorber. you could change the format onto font. That makes that easier to see through. So you've added that. Now the important bit is to change the composition or add in a composition. So I'm going to just say, just define a composition actually. So I'm just going to say 0.67 of methane. 0.67 of methane. I'm going to say 0.23 of ethane, and I'm going to assume 0.1 mole percent water. What the composition comes up as, and I'm going to say okay on that. That goes in quite well. That's really good. So that's done actually. I'm just going to put that on a hold so that we can solve that after we've added the absorber column. Next step is to add a column to this, and you want to add an absorber column. Same thing. I think there's an easier way of doing this. I'm just going to minimize this out. I'm going to move this up here. Some reason, yeah. Change that. Right, I'm just going to rename that. So I'm just going to say tech underscore absorber. Just going to change the font size again. I think you could define that earlier as well anyway. So did that. So I'm going to define a few more streams to it. I minimize the object palette. I'm going to bring that back up again. So I've gone to the common side. So I'm just wanting to add a material stream. Um, this is the gas outlet of it. This is the liquid outlet of it, and I want to add another stream which is going to be the inlet to the top of the column, which is the tech actually, because you need tech to come in to dehydrate the gas which is coming through the um, through from the first separation actually. So this is going to be the vapor of the sales gas. Yeah, that's done. This is going to be the liquid flowing out, and that's going to be changed that to fine. And this is going to be the lean tech which is coming in into the absorber. Let's change that to 5. So that's basically going to be the rich tech which is going to come out. Yeah. This is going to be the lean tech which is going to be coming in. You just have to connect them all to the absorber column. So the top stage inlet is going to be our lean tech. The number of stages, I'm going to say 3 to it, just as an example. It's not responding. Hold on for a minute, guys. That's good. It's come back up again. Let's say 3 on it. Right. So if you can't make it in the bottom stage inlet is going to be the gas to the absorber. Bottom liquid out is going to be the bridge tech. Overhead liquid out is going to be your sales gas. It's going to be top down. Let's say 3. Right, okay. So next onto it, and it asks for a top stage pressure and a bottom stage pressure. I'm going to give them a value that's going to be 6,880, and the bottom stage, again these are all assumptions, and that will all differ based on the assumptions you made to your arrival pressure at the FPSO for your term project. So yeah, let's say done on it. Close that off. Active. Link. So the absorber now looks like this. You've got a lean tech coming in, you've got sales gas going out of it, and you've got rich tech going out from the bottom side of it. I'm just going to go and change the number of stages of it. Yeah, that's done. The next bit is to enter the composition of the lean tech. Go up here, and you also need to enter the temperature and pressure which they are going to come in. For this example, I'm going to assume as temperature and pressure they normally come in at. I'm going to assume 41 degrees Celsius, and pressure, it's about 6,915 kilopascal, and the molar flow is going to be about 6.4 kg moles per hour. This is done. Now you need to give it a composition. I'm pretty sure we are going to not have any methane and ethane, and we're going to definitely have tech to it, and that's going to be about 99.04%. So 0.9904, sorry, 90, yeah, 0.9904. That is correct. That's an assumption which we are making, and that's a common assumption in the industry. That's what they use. That's the purity of tech they use to dehydrate the natural gas. And then the remaining is going to be water. That's going to be 0.0096. Say okay on that. Good. Enter that. Calculates all that bit here, and I think we've entered what we had to now. All we need to do is just run this bit here, which will converge, which is converged here. So that's basically the end of the simulation. Now if you go up onto this bit here, now you could see the wet gas coming in, and we defined the temperature, pressure and the molar flow, and the Hysys itself calculated the phase split based on the pressure and temperature. So this resulted in the gas phase, and if you look at that, so that's going to be vapor, and it says 35 35 degrees Celsius and 69 bar. You get a certain mass flow of gas flowing through, and then you can look at the composition as well. So this is the composition that's being entered, and if you look at the sales gas bit here, it says it's all vapor, and that's the temperature and pressure. It's calculated based on the pressure we given to it in the distillation column, as well as the lean take. It comes in at a certain pressure as well. And then here you could see just methane and ethane going out. There is not much of water in it. That's exactly what we wanted out of the simulation. We wanted to remove water out of the simulation. And the other bit which we've not shown in this Hysys simulation is the tech dehydration is a recycle loop. So there's going to be a recycle loop which is going to be running to generate the lean tech out of the rich tech which we get from here. So the lean tech which comes over at the top of the column will be regenerated within a loop here, and that's not been shown, as that's not the intent of our tutorial. Our intent of our tutorial is just to show the glycol dehydration, how it's being used and how we model it. But in real field life and in industry, we would be having a recycle loop that will work on to convert this rich tech to lean tech, and the cycle will continue on and on. Thereby we can improve the efficiency and recover this rich tech, recover lean tech from this rich tech. So that's what we've got on for today. Thank you.